Hello, welcome to new video. In last video I discussed about how to load and initialize a program into the memory in Linux environment. So today we will be looking how to view a program footprint in memory. This is the layout of a program in memory. This one already discussed in last video. So here we can see that there is a code segment, data segment, heap and stack, and the entire program will be assigned to the process managers. And there will be a process descriptor for each program. So today we will be looking how to view this layout in a Linux environment. As shown in this slide, so for each program there is a unique ID, so called the process ID. In short, we call it as a PID. The PID can be fetched within the program by using a system called getPID. So I will be using this getPID system call to print out the process ID. So what we are using here, actually Linux provides a virtual file system called process file system, through which user can fetch process related information. So we will be looking how this process related memory layout fetched from the memory in a Linux environment. Here this is the short program I created to explain the concept. So this one is a short C program. So initially the first line it is printing the printing some text, and then it is printing the PID process ID. Here I am using the get PID system call. So in order to use this system call, the in the header file unistd has been added here, and then I stopped the function stopped this program by using the get core. So whenever this line hit, it waits for a character from the input, so the program will stop, wait for IO here. So at this time I will be after executing this one, the program will stuck waiting for the input from the input. At this time I will be going into the proc file system and then use the process ID to display the memory map, so we can see it. Yeah, so now we can see that the program is executed and it printed out the PID. Currently the process ID is 11019, and then the program is waiting for an input from the keyboard. So at this time I'm opening a parallel window here. So right now it is in proc, so I'm stepping back. So this is the place, the proc. Here we can see the different folders. So right now our PID is 11019. So here there should be a folder with the PID. So we can check it, 11019. Yeah, this is the process folder corresponding to our PID. So here I am stepping into this. So here we can see that there are a lot of information, task, scheduler, those are some of them. So a lot of information is related to this process we can find it here. So here I'm using the maps file. So this one will contain the memory map. So let's see what is inside the map. So there is a permission issue. So in order to access this, we need to have the super user privilege. Yeah, now we can see the memory map of this program. The left side the program is running and it is waiting for a keyboard input. At this time I printed out the live footprint of this program in memory. So we can see that there is a read and executable. So this is actually the code segment, and there are read only and then read write segments. Then the shared library you can see here, libc.so, also linked to the virtual address space of this program. And there is another library, linux x86 64.so.2, that one is also linked. So here we can see that there are some sections are read-only sections. Those are data. Some sections are read and execute permissions. So those are for sure code. And then read write sections are also there. Um, those are actually the uh, data. And apart from that, the usual and the sections, heap and also the stack can be visible. So these heap, stack, data segment and code segment, everything we can view here. So other than that, there are some special memory sections also be available. Those sections are vvar, vdso and vsyscall. Those are all some special memory sections related to this process. Next we see what are those special memory regions. The one of them is the VDSO. This means virtual dynamically linked shared object. This is actually to execute certain functions like get time of day at user pace. So these are actually the system calls. So in order to speed up the execution, so this library provides a user level binding. So for that, this VDSO, virtual dynamically linked shared object section, has been used. And another one is a VVAR. This means virtual variables. This provides read-only access to kernel variables. So this actually combinedly work with the VDSO to speed up the system call. And there is a section vsyscall. This is actually the legacy system call interface. In latest Linux system, this section is not really used. So this one is there to maintain the backward compatibility. So currently most of the system calls are accessed through VDSO and vvar. So actually these are the live footprint of the memory. So right now I'm trying to continue this program. I am hitting the keyboard key here. So the now the program got terminated. Now in case suppose we try to print out this, we see that there is nothing, no such process. So that means the process has been terminated right now. So this is a short video how to view a program's live footprint in memory in Linux system. So thank you for watching. If you like this video, just give a thumbs up and put a comment. Thank you all.